On November 23, 2023, a detector in the United States picked up a signal lasting barely a tenth of a second. That tiny blip in the data represented the final moments of a collision between two black holes. A collision that happened more than 7 billion light-years away, more than halfway across the observable universe. The signal was unusual for many reasons, but the most striking one was this. According to our best models of stellar physics, neither of those two black holes should have been able to exist in the first place. That is not a figure of speech. The masses involved fall squarely into what astrophysicists call the mass gap, a range of black hole sizes that current theory says nature cannot produce. And yet the signal was real, confirmed by a second independent detector on the other side of the country, and the probability of it being random noise was estimated at less than once in 10,000 years of continuous observation. This one event has forced scientists to reconsider some of the most fundamental assumptions they hold about how the most massive objects in the universe are born. To understand why this collision is so significant, we need to start with some background, specifically with the technology that made detecting it possible at all. Black holes are, by their very nature, invisible. Their gravity is so extreme that not even light can escape from within the boundary known as the event horizon. They emit no radiation that we can directly see or measure in the conventional sense. For most of history, we could only infer the existence of black holes from their gravitational effects on surrounding matter, the way they pulled stars into tight orbits, or heated gas clouds to extreme temperatures as materials spiraled inward. Detecting a collision between two black holes directly, from billions of light-years away, was considered essentially impossible for most of the 20th century. What changed that picture was a prediction made by Albert Einstein more than 100 years ago, one that Einstein himself believed could never be tested. Einstein's general theory of relativity, published in 1915, described gravity not as a force, but as a curvature of spacetime, the four-dimensional fabric of the universe that combines the three dimensions of space with time. In this picture, massive objects warp the geometry of spacetime around them, and other objects move along the curves created by that warping, which is what we experience as gravitational attraction. A direct consequence of this theory is that when a massive object accelerates through space, it should disturb the fabric of spacetime around it, much like the way a boat moving through water creates waves that spread outward in all directions. Einstein called these disturbances gravitational waves. The problem was scale. For ordinary objects, moving at ordinary speeds, the gravitational waves produced would be inconceivably small, far below the sensitivity of any instrument that could realistically be built. Even Einstein concluded that gravitational waves would remain forever beyond direct measurement. He was right that the technology of his era made detection impossible. What he could not foresee was the extraordinary precision that engineering would eventually achieve, or that one class of astrophysical event would produce gravitational waves powerful enough to actually detect. That class of event is the merger of two massive compact objects, black holes or neutron stars, in the final moments before they collide. When two black holes are gravitationally bound to each other, they orbit their common center of mass. Over time, and this can be billions of years, they lose energy by emitting gravitational waves, and their orbits gradually shrink. As the black holes spiral closer together, they move faster and faster. In the final fraction of a second before merger, they are moving at a significant fraction of the speed of light, and the gravitational waves they produce in those last few orbits are intense enough just barely to be measured at astronomical distances. The detector that made this measurement possible is called the Laser Interferometer Gravitational Wave Observatory, or LIGO. It consists of two separate facilities in the United States, one in Hanford, Washington, and one in Livingston, Louisiana, positioned about 3,000 kilometers apart. The design principle behind LIGO is conceptually elegant, though the engineering required to realize it is almost incomprehensibly precise. Each facility consists of two long corridors arranged in an L shape, with each arm extending 4.5 kilometers in length. The tubes inside these corridors are evacuated to a pressure lower than the vacuum of outer space to prevent air molecules from scattering the laser beams. At the end of each arm hangs a mirror 40 kilograms of fused silica, polished to an accuracy measured in sub-nanometers and suspended from a chain of pendulums designed to isolate it from any vibrations in the ground. A laser beam is split and directed down both arms simultaneously. The beams bounce back and forth between the mirrors, effectively traveling a distance of over 1,000 kilometers before being recombined, and the recombined beam is analyzed for any difference in the distance traveled down each arm. When a gravitational wave passes through the detector, it stretches space in one direction and compresses it in the perpendicular direction, then alternates. This means one arm of the detector gets very slightly longer while the other gets very slightly shorter. Then they switch. The laser can detect this change. How small is the change? For a typical gravitational wave event, the change in the length of each 4.5-kilometer arm is about 1,000th the diameter of a proton. A proton is already roughly 100,000 times smaller than an atom. LIGO is measuring a change in distance equivalent to 1,000th of that. This is among the most precise measurements ever made by any instrument in the history of science. LIGO first detected gravitational waves in September 2015, observing the merger of two black holes roughly 1.3 billion light-years away. The discovery confirmed the last major untested prediction of general relativity, and the physicists who led the project were awarded the Nobel Prize in Physics in 2017. Since then, LIGO and its partner observatories, the Virgo detector in Italy and Kagra in Japan, have collectively detected more than 300 gravitational wave events. The majority of these are black hole mergers, and together they have transformed our understanding of how black holes are distributed throughout the universe, how often they merge, and what masses they tend to have. Which brings us back to the November 2023 event, cataloged as GW231123. When the signal arrived, it registered on LIGO's instruments as a blip roughly 20 times louder than the typical background noise level. That alone marked it as significant. When the same signal was confirmed by the second detector in Louisiana, the team knew they had something real. Analyzing a gravitational wave signal is like reading a fingerprint. The shape of the waveform, how it rises and falls, how quickly it oscillates, how it decays, encodes information about the masses and spins of the objects involved, the distance to the event, and the geometry of the collision. Scientists run the observed signal against large banks of simulated waveforms, computed from the equations of general relativity to find the best match. For GW231123, the best matching models pointed to two black holes, both spinning very rapidly, that had merged to form a single black hole with a mass somewhere between 182 and 251 times the mass of our Sun. The signal itself appeared to capture only the second half of the merger, the so-called ring-down phase, during which the newly formed black hole vibrates and settles into a stable configuration, releasing a final burst of gravitational waves in the process. That final black hole mass is extraordinary. But what made this event truly puzzling were the masses of the two black holes before they merged. Based on the analysis of the waveform, each of the progenitor black holes had a mass, placing them squarely within the mass gap. The mass gap is not an arbitrary category. It is a prediction that emerges from detailed models of stellar evolution and the physics of supernovae explosions. To understand it, we need to understand how black holes form in the first place. The most common route to a stellar mass black hole starts with a massive star, typically one with more than 20 to 30 times the mass of our Sun. Throughout its life, the star burns hydrogen in nuclear fusion reactions in its core. Eventually, it exhausts its hydrogen and begins fusing heavier elements: helium, then carbon, then oxygen, silicon, and finally iron. Iron is the endpoint. Fusion reactions involving iron do not release energy, they consume it. When the core becomes predominantly iron, it can no longer generate the outward pressure needed to counteract the inward pull of its own gravity. The core collapses, sometimes in less than a second, bouncing to produce a shock wave that blasts the outer layers of the star outward in a Type II supernova explosion. If the remnant core left behind exceeds a critical mass, roughly 2 to 3 times the mass of our Sun, the maximum a neutron star can sustain, then even the pressure of tightly packed neutrons cannot halt the collapse, and the core continues to shrink into a black hole. This process works well for stars up to roughly 130 times the mass of our Sun. Above that threshold, something different happens. Very massive stars, those with between 130 and 250 solar masses, are subject to a runaway process inside their cores called pair instability. At the extreme temperatures inside these stellar giants, the high-energy gamma-ray photons that help support the star's core begin converting into pairs of electrons and their antimatter counterparts, positrons. This conversion removes energy from the radiation pressure that was helping hold the star up. The core begins to contract. The contraction triggers explosive nuclear burning, generating a violent outward blast. For stars at the lower end of this range, This can happen in pulses the star ejects large quantities of its own mass in successive outbursts, called pulsational pair instability supernovae, gradually reducing its own mass until it is small enough to avoid the instability. The stripped-down remnant eventually collapses into a black hole, but by then it has lost so much mass that the resulting black hole is smaller than 50 solar masses below the mass gap. For stars at the upper end of this range, those with more than roughly 250 solar masses, the pair instability process is so powerful that the entire star is disrupted in a single cataclysmic explosion, leaving no remnant at all. Nothing collapses into a black hole. The star simply tears itself apart. The result of this physics is a gap. Stars between roughly 130 and 250 solar masses cannot produce black holes in the mass range of roughly 50 to 130 solar masses. The lower end of this gap is set by how much mass pulsating stars can shed before they collapse. The upper end is set by the threshold, above which the entire star is destroyed. Black holes in the mass gap cannot form through standard stellar collapse. They are, in this sense, theoretically forbidden. For nearly 10 years after LIGO began operations, this prediction appeared to hold. Gravitational wave detections consistently turned up black holes below 50 solar masses or in the supermassive range, with nothing detected in the gap. The theory seemed sound. Then GW 231123 arrived with two parent black holes sitting well within the forbidden zone. The immediate question was obvious. How did these objects form if standard stellar evolution cannot produce them? The first hypothesis scientists considered was hierarchical merging. In this scenario, the two large black holes had not formed from single stars. Instead, they had grown over time through a sequence of smaller black hole mergers, each collision adding to their mass and spinning them up. The black holes that collided in GW 231123 would themselves have been the products of earlier mergers, which were in turn products of even earlier ones. This kind of hierarchical merger chain is theoretically possible and is thought to occur in certain dense astrophysical environments. Globular clusters, ancient, densely packed, spherical collections of hundreds of thousands to millions of stars are candidates because the high concentration of stars means black holes can interact frequently and repeatedly. If the escape velocity from the cluster is high enough, a black hole produced by a merger will not be ejected before it can participate in the next one. However, this explanation ran into a problem when scientists examined the spin properties of the objects involved in GW 231123. Spin is one of the three fundamental properties of a black hole, alongside mass and electric charge. When two black holes merge, the resulting black hole inherits the combined spin of both parents. But the direction matters. Individual black holes in a cluster acquire their spins from different formation processes and orbital histories, so their spin axes tend to point in random directions. When two randomly oriented, moderately spinning black holes merge, their spins partially cancel each other out. The average spin magnitude of a daughter black hole produced through hierarchical mergers is typically quite modest. The two black holes in GW 231123 were spinning at close to the speed of light. This makes them the fastest spinning black holes ever confidently detected in a gravitational wave event. If they had grown through hierarchical mergers, there would need to be an exceptional sequence of unusually high spin parents, or some other mechanism boosting the spin at each step. Simple statistical averaging makes this explanation increasingly unlikely, with each generation of mergers required to reach such extreme spin values. Hierarchical merging alone could not convincingly account for both the high masses and the extreme spins simultaneously. Scientists needed a different explanation. The new theory that emerged came from researchers at the Flatiron Institute's Center for Computational Astrophysics, led by Or Gottlieb. Their work introduced a mechanism that had been underappreciated in models of black hole formation: the magnetic fields of the parent stars. When a massive star forms a black hole, there is a brief but critical period during which the black hole is surrounded by a cloud of stellar debris, gas, and dust from the star's outer layers that did not fall in immediately during the core collapse. The properties of this debris cloud and the fate of the black hole depend on several factors that had previously been modeled in simplified ways. Gottlieb's team built detailed computational simulations of a star with 250 solar masses and followed its evolution from the moment it began fusing hydrogen through to its eventual collapse and the aftermath of the supernova. One of the first things the simulation revealed was that the star would burn through a substantial portion of its own mass as fuel over its lifetime. By the time it reached collapse, A 250 solar mass star would have shed enough material to arrive at a pre-collapse mass of roughly 150 times the mass of the Sun, placing it just above the upper edge of the mass gap. That puts it in a regime where collapse might produce a black hole, rather than being completely disrupted. The next step was to model what happened after the collapse. The team considered two scenarios. In the first, the parent star was not rotating significantly. In this case, the surrounding debris cloud fell more or less symmetrically into the central black hole. The black hole grew in mass, but the process was relatively straightforward, and the spin values of the resulting black hole were relatively modest. In the second scenario, the parent star was rotating rapidly. This changes everything. The debris cloud does not fall in symmetrically. Instead, conservation of angular momentum causes it to flatten into a rotating accretion disk around the young black hole, similar to the disks observed around quasars and active galactic nuclei at the centers of galaxies. This is where the magnetic fields become critical. The stellar material surrounding the black hole carries with it the magnetic fields that were threaded through the original star. As this material spirals inward onto the accretion disk, the differential rotation wins and amplifies these magnetic fields to extreme intensities. The amplified fields exert pressure on the disk material, and in some configurations, they can drive powerful jets of plasma, streams of charged particles moving at close to the speed of light, launched perpendicular to the plane of the disk and away from the black hole. This process is well established observationally. We see these relativistic jets emerging from the centers of active galaxies and quasars across the universe. What Gottlieb's team showed is that this same process can occur immediately after a black hole is born from a collapsing massive star. The jets carry away energy and material from the environment around the newborn black hole. In cases where the magnetic fields are very strong, the team found that up to half of the original stellar mass that would otherwise have fallen into the black hole can instead be blasted away in these jets. The black hole ends up significantly less massive than it would have been without the magnetic fields. This creates a pathway to black holes in the mass gap. A very massive star, one that starts at 250 solar masses, but loses mass over its lifetime, to arrive at 150 solar masses at collapse, can, in principle, produce a black hole in a mass range that would otherwise be forbidden if the magnetic field-driven jet mechanism removes the right amount of infalling material. The same simulations revealed a second mechanism that addresses the spin problem. When the magnetic fields generate explosive outbursts, pushing material away from the black hole in bursts rather than a steady flow, each outburst imparts a small kick to the black hole, altering its angular momentum. This stochastic momentum transfer, accumulated over many outbursts, can spin the black hole up to very high values. The key finding was that the strength of the magnetic field determines both the mass and the spin of the resulting black hole in a correlated way. Strong magnetic fields drive away more material and also impart larger spin kicks. But because they are blasting away so much mass, they tend to produce lighter, faster spinning black holes. Weaker magnetic fields allow more material to fall in, producing heavier black holes. But the spin kick effect is less pronounced, and the resulting spin magnitude is lower. This correlation between mass and spin, mediated by the magnetic field strength, is a specific, testable prediction. If confirmed by future observations, it would be a new fundamental relationship governing how black holes are born. The Gottlieb team's simulations can reproduce the properties of the black holes involved in GW 2, 3, 1, 1, 2, 3, both the masses that fall within the gap and the extreme spin values without requiring an unrealistic sequence of hierarchical mergers. The mechanism is physically motivated by processes we observe in other contexts, specifically the jet launching behavior of accreting black holes in galactic nuclei. There are additional observational implications of this theory that make it particularly attractive from a scientific standpoint, because they offer ways to test it independently of gravitational wave data. The magnetic field-driven explosions that spin up and shape the newborn black hole should also produce detectable electromagnetic signals. Specifically, the relativistic jets powered by these intense magnetic fields would generate very energetic flares of radiation events similar to short-duration gamma-ray bursts. These bursts are among the brightest events in the known universe, visible across cosmological distances. If the formation mechanism proposed by Gottlieb and colleagues is correct, then some fraction of the gamma-ray bursts detected by space-based observatories should correspond to black hole births in the mass gap. Identifying and correlating gamma-ray bursts with gravitational wave events in future observations could provide independent confirmation that this formation channel is operating in nature. This would require the next generation of both gravitational wave detectors and gamma-ray telescopes to work together. Currently planned upgrades to the LIGO and Virgo detectors, as well as the proposed Einstein telescope in Europe and Cosmic Explorer in the United States, would dramatically increase sensitivity and detection range. The next generation of high-energy gamma-ray observatories could provide the complementary electromagnetic coverage needed to catch these signatures. There is a broader context to why the mass gap matters beyond any single event. For decades, astronomers recognized two broad categories of black holes. Stellar mass black holes, ranging from roughly 5 to 100 solar masses, form from the collapse of individual massive stars. Supermassive black holes, ranging from millions to tens of billions of solar masses, inhabit the centers of most large galaxies and are thought to have grown over cosmic time through a combination of mergers and accretion. Between these two populations, there has long been a suspected class of objects known as intermediate mass black holes, ranging from roughly 100 to 100,000 solar masses. These would serve as a natural bridge between stellar mass and supermassive black holes. However, direct evidence for them has been historically scarce. Part of the reason is precisely the mass gap. If the range between 50 and 130 solar masses is genuinely empty, then the bottom of the intermediate mass range is poorly populated, and the conventional formation channel through stellar collapse is blocked. GW 231123 represents the clearest direct evidence yet for a black hole in this intermediate mass range, and the theoretical work it has motivated suggests that the mass gap may not be truly empty. If the magnetic field formation mechanism is correct and operates with a range of efficiencies across different stellar systems, then intermediate mass black holes could be scattered throughout the universe in environments that are just difficult to observe inside dense star clusters, at the centers of dwarf galaxies, or floating freely in intergalactic space after being ejected from their birth environments. Understanding how many intermediate mass black holes exist, where they are located, and how they form is important for understanding the complete evolutionary history of black holes in the universe, including the question of how supermassive black holes themselves grew to their extraordinary sizes. One leading idea is that supermassive black holes grew through mergers and accretion, seeded by smaller precursors. If intermediate mass black holes are abundant, they could represent those seeds, and the magnetic field-driven formation channel could be one of the mechanisms that produced them in large numbers in the early universe. The early universe is particularly relevant here. The most massive stars, the kind needed to produce intermediate mass black holes, through the mechanism proposed by Gottlieb and colleagues, were more common in the early universe when the interstellar gas was less enriched with heavy elements. Massive stars in the present-day universe lose significant fractions of their mass through stellar winds driven by the radiation pressure on heavy elements in their atmospheres. In the metal-poor early universe, these winds were weaker, and stars could retain more of their initial mass. Stars with 200 or 250 solar masses were more likely to reach the end of their lives with enough mass to potentially produce intermediate mass black holes through collapse. This means that if the proposed mechanism is real, its effects would have been strongest in the early universe, when conditions were most favorable for producing very massive stars. The intermediate mass black holes produced in that era could then have served as the early seeds of the supermassive black holes we observe today at the centers of large galaxies. This connection between a gravitational wave event detected in 2023 and the origin of supermassive black holes at the dawn of cosmic history is one of the reasons GW 231123 has attracted such attention within the astrophysics community. There are still significant uncertainties in the interpretation of the event. The analysis of gravitational wave signals involves statistical inference rather than direct measurement, and for an event like GW 231123, where only the ring-down phase was clearly detected, rather than the full in spiral and merger, the constraints on the parameters are broader than for a typical event. The estimated mass range of the final black hole spans from 182 to 251 solar masses, which is a wide range reflecting genuine uncertainty. The high spin values inferred from the signal are also subject to interpretation. Extracting spin information from gravitational wave signals is technically challenging. particularly when the full waveform is not available. Some researchers have questioned whether the spin analysis is robust enough to rule out the hierarchical merger hypothesis definitively. These are genuine scientific debates, and they are part of the normal process of evaluating an unusual and significant result. The fact that two independent detectors both recorded the same signal with the same characteristics provides strong evidence that the event was real. The task of precisely characterizing its properties will continue as the community applies additional analysis techniques. One important tool for improving confidence in results like this is the growing catalog of gravitational wave detections. With more than 300 events now recorded, patterns in the mass and spin distributions of merging black holes are becoming apparent. If the Gottlieb formation mechanism is operating in nature, it should produce a population of black holes with a characteristic correlation between mass and spin. Heavier black holes spinning more slowly, lighter ones spinning faster. Future detections at intermediate masses could test whether this pattern holds. The LIGO Observatory and its partners have been running in successive observing runs, with hardware upgrades between runs steadily increasing sensitivity. The most recent run, designated 04, began in May 2023 and is expected to deliver hundreds of additional gravitational wave detections. Within that dataset, there may be additional events in or near the mass gap that could provide supporting or contradictory evidence for the magnetic field formation hypothesis. Beyond this, next-generation detectors are already in the planning and design phases. The Einstein telescope, proposed to be built underground in Europe to reduce environmental noise, would be sensitive to gravitational waves at lower frequencies than LIGO, enabling it to detect the early in-spiral phase of massive black hole mergers far earlier and at greater distances. This would provide richer waveform data that is less ambiguous to interpret. Cosmic Explorer, the American next-generation concept, would have arms 10 times longer than current LIGO, reaching 40 kilometers, and would be sensitive enough to detect nearly every black hole merger in the observable universe. These instruments are not expected to come online until the mid-2030s, but when they do, they will transform gravitational wave astronomy from a field where notable events are counted in the hundreds to one where they are counted in the millions. The statistical power of that dataset would allow definitive tests of formation theories that are currently speculative. Beyond gravitational waves, the hunt for intermediate mass black holes is also advancing through conventional electromagnetic astronomy. Several candidate intermediate mass black holes have been identified in globular clusters based on the dynamics of stars near their centers, stars moving as if they are being gravitationally influenced by an unseen massive object. These detections are not yet considered definitive, but they are suggestive. X-ray observations of ultraluminous X-ray sources, extremely bright X-ray emitters found in some nearby galaxies, have also been interpreted by some researchers as accreting intermediate mass black holes, though other explanations are possible. The combination of gravitational wave data, X-ray observations, stellar dynamics, and gamma-ray detections represents a multi-messenger approach that is increasingly defining modern astrophysics. No single observational technique tells the complete story, but taken together, they can constrain models in ways that individual observations cannot. There is something worth stepping back to consider in all of this. The detection of gravitational waves was itself considered impossible within living memory. The LIGO detectors were built over decades, continuously refined, and operated for years before making their first detection. That first detection, in September 2015, immediately became one of the most significant scientific achievements of the 21st century. Less than a decade later, the technology is mature enough that detecting black hole mergers across billions of light years has become almost routine. So much so that an event like GW231123 stands out not because it was detected, but because of what it revealed. The story of GW231123 is also a story about the limits of theoretical confidence. The mass gap was not a vague intuition or a rough guideline. It was a specific, quantitative prediction derived from detailed models of nuclear physics, stellar evolution, and the dynamics of supernova explosions. It had held up against observational data for years, and then a single event provided evidence that, in some cases at least, the prediction was wrong, or more precisely, that there exists a formation channel the theory had not adequately accounted for. This is not a failure of the theory. It is an invitation to refine it. The magnetic field mechanism proposed by Gottlieb and colleagues does not overturn our understanding of stellar physics. It adds to it by accounting for a class of phenomena the role of strong magnetic fields in shaping the immediate post-collapse environment that had been underweighted in earlier models. What remains unknown is how common this formation channel actually is. The signal, GW231123, is, as of this writing, the only confirmed example of black holes merging in the mass gap. One event is not enough to establish a distribution. It could represent an extremely rare exception to general trends. Or it could be the first of many such detections that will reveal a population of intermediate mass black holes hiding throughout the universe. What the next several years of observations will hopefully answer is whether the properties of this event, the specific combination of masses and spins, are a consistent signature of magnetic field-driven formation, or whether they are an idiosyncratic outcome of unusual initial conditions. If future gravitational wave detectors find more events with similar characteristics, the theoretical framework developed in response to GW231123 will become much more robustly established. There is also the question of the long-term fate of black holes formed through this mechanism. If intermediate mass black holes are produced in substantial numbers in dense stellar environments, they will continue to evolve through interactions with their surroundings, merging with other black holes, accreting gas from molecular clouds, and contributing gravitationally to the dynamics of the star clusters and galaxies they inhabit. Tracing the complete evolutionary history of these objects, from birth in the core collapse of a massive star to eventual incorporation into a supermassive black hole at the center of a galaxy, is one of the outstanding problems of extragalactic astrophysics. The field of gravitational wave astronomy is only about 9 years old. It began in 2015 with the detection of 2 merging black holes, a result that confirmed a century-old theoretical prediction and opened an entirely new observational window on the universe. In that short time, it has already produced multiple Nobel Prize-level discoveries, revealed the existence of neutron star mergers and the heavy elements they create, and now presented us with an object that our most carefully developed theories said could not exist. The mass gap is no longer unambiguously empty. The question is now not whether intermediate mass black holes exist, but how they form, how common they are, and what role they have played in shaping the universe we observe today. The signal from November 23, 2023, lasted a tenth of a second. The scientific questions it has raised will keep researchers occupied for decades. To fully appreciate the significance of what LIGO detected in November 2023, it is worth spending more time understanding the instrument itself and the scientific culture that built it. The idea of detecting gravitational waves using laser interferometry was first seriously proposed in the 1970s by Rainer Weiss at the Massachusetts Institute of Technology. Weiss sketched out the basic concept in a technical report in 1972, describing how a carefully designed laser interferometer could, in principle, detect the fractional changes in length caused by passing gravitational waves. The concept was elegant. The practical challenges were staggering. The fundamental problem is noise. Everything vibrates. The ground shakes from distant traffic, ocean waves, human footsteps, thermal fluctuations in the mirror coatings, quantum fluctuations in the laser light itself. Any of these noise sources can mimic or overwhelm the signal from a gravitational wave if not carefully controlled. The LIGO team spent decades developing solutions to each of these noise sources in sequence. The seismic isolation systems for the mirrors are engineering masterpieces, multi-stage pendulums within pendulums, with active feedback control systems that continuously monitor and compensate for ground motion. The vacuum systems inside the detector arms achieve pressures around 1/millionth of a billionth of atmospheric pressure. The laser power is stabilized to better than 1 part in 10 million. The mirror coatings are designed to absorb less than 1 part per million of the incident laser light. Even after all these measures, LIGO regularly detects what are called glitches brief, anomalous noise events caused by everything from nearby earthquakes and lightning strikes to passing trucks. The requirement for 2 detectors separated by thousands of kilometers is specifically designed to distinguish real gravitational wave signals, which should arrive at both detectors within the light travel time between them, from local noise events, which should not. Building this instrument took approximately $1 billion and decades of work by thousands of scientists and engineers across multiple countries. The investment was justified on scientific grounds. Gravitational wave astronomy would open an entirely new window on the universe, but for much of the construction period, there was genuine uncertainty about whether the instrument would be sensitive enough to detect anything at all. The first generation of LIGO detectors, which operated from 2002 to 2010 did not detect any gravitational waves. The second generation, upgraded with significantly improved sensitivity and renamed Advanced LIGO, detected the first event in its very first observing run, just 2 days before the formal beginning of observations. That first detection, designated GW150914, was a binary black hole merger that produced a signal lasting about 0.2 of a second in the sensitive frequency band of the detector. The characteristic chirp a brief rising tone as the two black holes spiraled faster and faster before merging was immediately recognizable to the team that had been searching for it for decades. The signal was so clean, so precisely matching the theoretical template, that several members of the team initially suspected an injected test signal. It was not. It was real. In the years since, LIGO and its partners have cataloged an enormous diversity of events. There have been black hole mergers involving objects of very different masses, producing asymmetric, more complex waveforms. There have been neutron star mergers, which in addition to gravitational waves produced a burst of gamma rays, ultraviolet light, optical light, infrared light, and radio waves that were observed simultaneously by telescopes around the world. An event known as GW170817 that demonstrated for the first time that neutron star mergers are one of the primary sites where gold, platinum, uranium, and other heavy elements are forged in the universe. There have been what appear to be mergers between neutron stars and black holes, and now there is GW231123, which has revealed black holes that theoretically should not exist. Each of these events has contributed to a deepening picture of the compact object population of the universe. What is becoming clear is that this population is more diverse and more complex than the simplest theoretical models predicted. There are more black holes with unusual mass ratios, more events at unexpected mass scales, more spin configurations that challenge simple formation scenarios. This diversity is, from a scientific standpoint, encouraging. It means there is more physics operating in these systems than our models had captured. Every anomalous event is an opportunity to refine the theory. The spin properties of merging black holes deserve particular attention here, because spin is one of the most information-rich quantities accessible through gravitational wave observations, and one of the most difficult to predict from first principles. A black hole's spin is characterized by its dimensionless spin parameter, which ranges from 0 for a non-rotating black hole to 1 for a black hole rotating at the theoretical maximum, where the event horizon itself would be moving at the speed of light. Real astrophysical black holes are thought to span this entire range, depending on their formation history and subsequent accretion. Black holes formed from the direct collapse of a slowly rotating stellar core are expected to have low spin parameters. Black holes that have accreted significant amounts of material from a companion star, with the accreted material spinning in a consistent direction, can be spun up to high values over time. And black holes formed from the merger of two other black holes inherit the combined angular momentum of their progenitors, modulated by the directions and magnitudes of each. The extreme spin values observed in the two black holes involved in GW231123, close to the maximum theoretical limit, are not naturally explained by any of the standard scenarios. Stellar collapse without a mechanism to preferentially spin up, the remnant typically produces modest spins. Accretion over extended periods is plausible for some high-spin systems, but the binary nature of the system and the environment required to host it make that scenario complicated. The magnetic field kick mechanism proposed by Gottlieb's group is notable precisely because it offers a physical pathway to high spin during the formation process itself, without requiring either extended accretion from a companion or a series of carefully orchestrated mergers. The kicks imparted by episodic magnetic field-driven outbursts during the collapse add angular momentum stochastically, and the simulation showed that cumulative kicks can drive the spin parameter to values approaching the maximum. Understanding the spin distribution of the overall black hole population is one of the major goals of future gravitational wave observations. If the Gottlieb mechanism is operating broadly, it predicts a specific pattern in the joint mass spin distribution of black holes, a correlated trend that should be distinguishable from the distributions produced by other formation channels. With hundreds or thousands of events in the intermediate mass range, statistical tests of this prediction could become definitive. The technology of gravitational wave detection itself continues to evolve rapidly. The current LIGO detectors are limited at low frequencies by seismic noise and at high frequencies by quantum shot noise in the laser. Recent upgrades have introduced squeezed light technology, a technique from quantum optics that exploits quantum correlations between photons to reduce measurement uncertainty below what the standard quantum limit would suggest is possible. This has already improved LIGO sensitivity at certain frequencies and points toward further improvements in future observing runs. The third observing run, O3, which ran from April 2019 to March 2020, produced enough events to fill an entire catalog. The fourth observing run, O4, which began in 2023 and is ongoing, incorporates additional hardware improvements and the reintegration of the Kagra detector in Japan into the network. A larger detector network improves the ability to localize the sky position of gravitational wave sources, which is critical for coordinating follow-up observations with conventional telescopes. The ultimate goal of gravitational wave astronomy is to use the complete population of detected mergers as a cosmological probe. By measuring the gravitational wave signal from binary mergers, which encodes the luminosity distance to the source, and combining this with independent measurements of the recessional velocity of the host galaxy, it is possible to measure the Hubble constant, the rate at which the universe is currently expanding. This approach is completely independent of the traditional distance ladder methods used in optical astronomy, and it could help resolve the growing tension in Hubble constant measurements that has emerged in recent years. For this application to work, a large statistical sample of well-localized events is needed, together with secure host galaxy identifications. GW170817, the neutron star merger in 2017, provided the first gravitational wave measurement of the Hubble constant. The result was consistent with both the early universe and late universe measurements, but with a large uncertainty because it was a single event. With dozens or hundreds of similar events with identified host galaxies, the precision would improve dramatically. Black hole mergers without electromagnetic counterparts are more challenging to localize and identify with host galaxies, but statistical methods using the distribution of possible host galaxies within the localization volume can still provide useful cosmological constraints when applied to large samples. The scientific program enabled by gravitational wave astronomy thus extends far beyond black hole physics. It touches on nuclear physics through the equation of state of dense neutron stars, on nucleosynthesis through the heavy element production in neutron star mergers, on cosmology through independent Hubble constant measurements, and on fundamental physics through tests of general relativity in the strong field regime. GW231123 is one node in this vast and growing network of scientific connections. It is significant individually for the questions it raises about the mass gap and the formation of intermediate mass black holes, but it also belongs to a broader program of observation that is systematically transforming our understanding of the universe at its most extreme. What makes gravitational wave astronomy uniquely powerful is that it observes a completely different physical phenomenon than all other forms of astronomy. Electromagnetic observations, whether radio, infrared, optical, ultraviolet, X-ray, or gamma ray, all rely on photons, the carriers of the electromagnetic force. Gravitational waves are carriers of gravitational information, and they interact with matter in an entirely different way. Photons are absorbed and scattered by intervening gas and dust. Gravitational waves pass through virtually everything unimpeded. The universe is essentially transparent to gravitational waves, which means that gravitational wave observatories have access to sources and environments that are completely hidden from electromagnetic telescopes. The center of our own galaxy, obscured by dense clouds of dust and gas that block most forms of electromagnetic radiation, is an open book to gravitational wave detectors. The early universe, before the moment of recombination, approximately 380,000 years after the Big Bang, when it first became transparent to light, is inaccessible to electromagnetic telescopes, but potentially detectable through primordial gravitational waves, waves produced in the very earliest moments of cosmic history. Current ground-based detectors are not sensitive to the lowest frequency gravitational waves, where many of the most interesting sources lie. Supermassive black hole binaries in merging galaxies produce gravitational waves at frequencies of millionths or billionths of a hertz, far below the millihertz to kilohertz range, accessible to LIGO. Detecting these ultra-low frequency waves requires a space-based detector, and one such detector, called LISA, the Laser Interferometer Space Antenna, has been approved by the European Space Agency and is currently under development, with a planned launch in the mid-2030s. LISA will consist of 3 spacecraft arranged in an equilateral triangle with sides of 2.5 million kilometers, exchanging laser beams to measure distances with extraordinary precision. It will be sensitive to sources involving supermassive black holes, including the mergers of the black holes at the centers of colliding galaxies, and the gradual in-spiral of smaller, compact objects into supermassive black holes. These observations will provide a completely new view of the most massive objects in the universe and probe the physics of spacetime in the strongest gravitational fields that currently exist. The next few decades of gravitational wave astronomy will be transformative. The combined observations from upgraded ground-based detectors, next-generation instruments, and space-based observatories will build a comprehensive statistical picture of black holes across every mass scale, from the stellar to the supermassive. Within that picture, the intermediate mass range, the domain of objects, like the black holes in GW 231123, will occupy a crucial position. There is also a deeper conceptual question lurking behind the specific physics of GW 231123, and it is worth spending some time on it directly. The mass gap was predicted theoretically before gravitational wave detectors had sufficient sensitivity to search for objects in that mass range. It was a prediction that emerged from our models of stellar evolution and the pair instability supernova mechanism. Those models were, and remain, well grounded in physics. The nuclear physics of pair production at high temperatures is well understood. The dynamics of thermonuclear runaway in the stellar core are captured in detailed numerical simulations. The prediction was not speculative. It rested on a deep foundation, and yet the prediction was incomplete. It failed to account for the full range of physical processes operating during and immediately after stellar collapse. The magnetic field mechanism, the twisting and amplification of stellar magnetic fields in a rapidly rotating accretion disk, driving relativistic jets and stochastic spin kicks, is also well understood physics in a different context. We observe these jets in active galactic nuclei and quasars. The physics of magnetohydrodynamics that governs them is not new. What was missing was the application of this physics to the specific circumstances of a collapsing, very massive star. This kind of gap, where physics that is well understood in one context turns out to be relevant in another context where it had been overlooked, is characteristic of scientific progress. It is less dramatic than the discovery of entirely new physical laws, but it is often more consequential in terms of expanding the range of phenomena we can explain. The history of astrophysics is full of examples. The mechanisms behind supernova explosions themselves are still not fully understood. We know they happen, and we have sophisticated simulations that can reproduce many of their observed properties, but the precise chain of events that turns an inward collapsing stellar core into an outward propagating shockwave is still an active research area. The role of neutrino energy deposition, convective instabilities, and magnetic fields in driving and shaping the explosion is being refined with each new generation of simulations. Neutron star physics provides another example. Neutron stars are the densest objects in the universe that are not black holes, containing more than the mass of our sun, compressed into a sphere roughly 20 kilometers across. The equation of state of matter at these densities, how pressure relates to density in conditions far beyond anything achievable in terrestrial laboratories, is one of the outstanding unsolved problems in nuclear physics. Gravitational wave observations of neutron star mergers, combined with measurements of neutron star masses and radii through X-ray observations, are currently providing the most precise constraints on this equation of state that have ever been available. Black holes, despite being simpler in a formal sense, characterized entirely by mass, spin, and charge, still host profound open questions. What happens to information that falls into a black hole? According to quantum mechanics, information cannot be destroyed. According to classical general relativity, it appears to be permanently hidden behind the event horizon. This tension, known as the black hole information paradox, remains unresolved after decades of theoretical effort. The interior of a black hole, the region inside the event horizon, is described by general relativity as containing a singularity, a point of infinite density where the theory breaks down. Most physicists believe this singularity is an artifact of applying a classical theory in a regime where quantum effects must be important. A complete quantum theory of gravity would presumably replace the singularity with something finite, but no such theory has been established. The singularity at the center of a black hole remains one of the most visible markers of the incompleteness of our current theoretical framework. These foundational questions are not directly addressed by the detection of GW 231123, but they provide the context in which black hole physics operates. Every observation of a black hole system, whether through gravitational waves, X-rays, or the direct imaging of the shadow of a supermassive black hole, accomplished by the Event Horizon Telescope in 2019 and 2022, adds data that can, in principle, constrain theories at the fundamental level. The Event Horizon Telescope deserves a brief mention here because it represents a complementary approach to studying black holes that is rapidly maturing alongside gravitational wave astronomy. The Event Horizon Telescope is not a single telescope, but a network of radio telescopes spread across Earth, all operating in synchrony to effectively create a radio dish the size of the planet. By combining signals from telescopes on multiple continents, the technique achieves the angular resolution needed to resolve the shadow of the central black hole in nearby galaxies. The first image, released in April 2019, showed the supermassive black hole at the center of the galaxy, Messier 87, an object roughly 6.5 billion times the mass of our Sun, surrounded by a glowing ring of superheated plasma falling inward. The second major result, in 2022, showed the black hole at the center of our own Milky Way, Sagittarius A star, which is about 4 million solar masses. These images do not directly study black holes in the stellar mass or intermediate mass range, but they demonstrate that we now have tools to observe the immediate environments of black holes with unprecedented detail. Future upgrades to the Event Horizon Telescope, including the addition of new stations and extension to higher frequencies, will sharpen these images further and potentially allow us to see the dynamics of the accretion flow and jet launching in real time. Coordinating Event Horizon Telescope observations with gravitational wave detections, if an intermediate mass black hole binary were to merge in a nearby galaxy and produce both a gravitational wave signal and an electromagnetic counterpart, would be an extraordinary scientific event. The probability of such a nearby event in any given observing period is small, but as gravitational wave detectors become more sensitive and monitor more of the sky, the chances increase. The multi-messenger approach, combining different types of observations of the same astrophysical event, is now a central strategy in observational astrophysics, and it was enabled in large part by gravitational wave astronomy. Before GW 170817, the neutron star merger in 2017, no event had ever been observed simultaneously in gravitational waves and light. That event triggered a global response involving roughly 70 spacecraft and ground-based observatories on every continent, operating across the entire electromagnetic spectrum from radio to gamma rays. The scientific harvest from that single event was extraordinary. It confirmed that neutron star mergers are the primary source of gravitational wave signals from compact object mergers involving neutron stars. It produced a kilonova, a burst of optical and infrared emission powered by the radioactive decay of heavy elements freshly synthesized in the merger, directly confirming that neutron star mergers are responsible for producing about half of all elements heavier than iron in the universe, including gold and platinum. It provided the first gravitational wave measurement of the Hubble constant, and it placed tight constraints on the speed of gravitational waves, confirming that they travel at the speed of light to a precision of better than 1 part in 10 to the 15th power. No comparable multi-messenger event has yet been observed for a black hole merger, because black hole mergers are not expected to produce significant electromagnetic signals in most scenarios. The exception would be if the black holes merge inside a dense gas environment, such as the accretion disk of an active galactic nucleus, in which case the merger and its gravitational recoil kick could disrupt the disk and produce observable flares of light. There are indeed a few candidate electromagnetic counterparts to black hole merger events in the LIGO catalog that have been identified in archival data from gamma-ray monitors operating at the time of the gravitational wave. Detections. None of these associations is considered definitive, but they are intriguing enough to motivate continued monitoring. For the GW 231123 event specifically, the magnetic field mechanism proposed by Gottlieb and colleagues predicts that the birth of the progenitor, black holes, should have been accompanied by gamma-ray bursts, observable across cosmological distances. At 7 billion light-years distance, a gamma-ray burst from the formation of these black holes would have been observable by space-based gamma-ray monitors. Whether any such events were recorded that match the sky location and timing is a question that the community is actively investigating. The sky localization of GW231123 is currently broad, as is typical for events where only the ring-down phase was detected and the full triangulation across multiple detectors was limited. Improving this localization through reanalysis of the data or through future detections of similar events with better coverage would help narrow the search for associated electromagnetic signals. All of these threads of investigation, the theoretical models, the detector improvements, the electromagnetic follow-up, the statistical analysis of the growing event catalog converge on a set of questions that define the scientific horizon for the next decade. How common are intermediate mass black holes? The answer requires many more detections in the mass gap, and probably the next generation of detectors to achieve this. What is the relationship between black hole mass and spin-at formation? The magnetic field mechanism predicts a specific correlation, testable with future observations. Are the progenitors of GW231123 indeed very massive stars formed in the early universe? Or do they represent exotic objects formed through other means? Electromagnetic observations of gamma-ray bursts could provide crucial evidence. Do intermediate mass black holes serve as seeds for supermassive black holes? This requires connecting the gravitational wave population to observations of the early universe with next-generation telescopes. Can we probe the interiors of black holes, or test general relativity in the strong field regime using the ring-down signal? GW231123 detected primarily the ring-down phase, making it potentially useful for such tests. But the signal-to-noise ratio and the limited waveform duration present challenges. These are not abstract questions. They connect to the most fundamental aspects of how the universe operates, how matter behaves under extreme conditions, how the largest structures in the cosmos formed, and whether our most successful theories of gravity and nuclear physics are truly complete. The universe has, as it has done many times before in the history of science, provided us with an observation that does not fit comfortably into our existing framework. The two black holes that collided somewhere in the universe 7 billion years ago, whose final ripples washed over a pair of detectors in rural Louisiana and Washington State in November 2023, have handed us a genuine mystery. The process of solving that mystery, designing better instruments, building more detailed simulations, connecting observations across different wavelengths and different physical channels, is the work of the next generation of physicists and astronomers. The mass gap is apparently not empty. The question now is, what fills it, how those objects formed, and what they can teach us about the cosmos. Let us return to the basics of what we know about the stellar populations that could produce the objects at the heart of GW231123, because understanding the progenitor stars in detail is essential to understanding why this event is so unusual and why the proposed theoretical explanations are physically reasonable. The most massive stars in the present-day universe are found in regions of active star formation, often at the cores of dense molecular clouds. The Tarantula Nebula in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, at about 160,000 light-years distance, hosts some of the most massive stars known. Stars in the cluster R136 at its center include several objects with masses estimated at more than 150 to 200 solar masses, making them among the heaviest stars currently known in the local universe. These stars are extraordinarily luminous, tens of millions of times more luminous than the Sun, and they live for only a few million years. By comparison, our Sun has a projected lifespan of about 10 billion years. The intense radiation from the most massive stars drives powerful stellar winds that strip material from the star's surface continuously throughout its lifetime. For stars with masses above about 40 solar masses in the present-day universe, these radiation-driven winds are so efficient that the star loses a significant fraction of its initial mass before it dies. A star that forms with 150 solar masses might arrive at the end of its life with 50 or 60 solar masses, dramatically changing what kind of remnant it produces. The efficiency of these mass-loss winds depends on the metallicity of the star, the fraction of its mass composed of elements heavier than hydrogen and helium. This is because the opacity of stellar material to radiation, which determines how effectively radiation can push material off the star's surface, depends on the presence of heavy elements. In a metal-poor star, the winds are weaker, and the star retains more of its mass. In the early universe, Essentially, all stars were metal poor, because heavy elements are produced in stellar interiors and disseminated through supernova explosions, a process that takes time. The very first generation of stars, known as population 3 stars, formed from gas that was essentially pure hydrogen and helium, with none of the heavy elements present in today's stars. These stars are thought to have been extraordinarily massive, with some theoretical models predicting typical masses of hundreds to thousands of solar masses. Population 3 stars have never been directly observed. They formed within the first few 100 million years after the Big Bang, and would have died long before any of our current telescopes could have been built to see them. But their deaths, which would have dispersed the first heavy elements into the pristine intergalactic gas, set the stage for all subsequent generations of stars and galaxies. The progenitors of the black holes in GW 231-123, if the magnetic field formation scenario is correct, do not necessarily need to be population 3 stars. They need to be massive enough and metal poor enough that their mass loss winds were weak and they retain sufficient mass to collapse into black holes in the intermediate mass range. Stars of 200 to 250 solar masses formed in metal poor environments, perhaps in dense star clusters in dwarf galaxies at high redshift, could fit this description. This connects the event GW 231-123 to some of the most active areas of observational cosmology. The James Webb Space Telescope, launched in December 2021 and operational since mid-2022, is observing galaxies in the early universe at redshifts of 10 and beyond, corresponding to times less than 500 million years after the Big Bang. These observations are revealing galaxies that are, in many cases, more massive and more structured than our pre-launch models predicted. Some of these early galaxies appear to host very active central black holes, possibly intermediate mass black holes, or even young supermassive black holes that are accreting matter at high rates. Understanding the connection between the metal-poor stellar populations in these early galaxies and the black holes they produce is one of the key scientific goals of the James Webb Space Telescope program. If very massive, metal-poor stars are common in the early universe, and if those stars can produce intermediate mass black holes through the magnetic field-driven formation channel, then the early universe may have been populated with far more intermediate mass black holes than current models suggest. The growth of these early black holes into the supermassive objects we observe today, black holes weighing billions of solar masses within the roughly 13 billion years of cosmic history, since the Big Bang is itself a challenging problem. Standard models of black hole growth through accretion are limited by the Eddington limit, a theoretical maximum accretion rate set by the balance between the gravitational pull of the black hole and the radiation pressure from the infalling material. Growing a black hole from a stellar mass seed to a supermassive one in a few 100 million years, as observations of high redshift quasars require, is difficult unless the seeds are already reasonably massive. Intermediate mass black holes, perhaps in the range of hundreds to tens of thousands of solar masses, formed through the collapse of very massive early stars, or through runaway mergers in dense early star clusters, provide more plausible seeds for rapid supermassive black hole growth. The existence of objects like those detected in GW 23-1123, if confirmed to be common in the early universe, would strengthen the case for the intermediate mass seed scenario of supermassive black hole formation. We are at a moment in astronomy where multiple independent lines of observation, gravitational wave detectors, space-based infrared telescopes, X-ray observatories, radio arrays are converging on the same set of questions about the origins and early evolution of black holes. The questions are being asked in different physical regimes, at different redshifts and mass scales, with different observational techniques, but they are all ultimately asking the same thing. How did the universe come to be populated with the objects we see today? And what processes govern their formation and growth? GW 23-1123 is one data point in this larger investigation, but it is a particularly valuable data point because it represents a direct detection, not a statistical inference, not an indirect gravitational signature, but a concrete measurement of the aftermath of a collision between two intermediate mass black holes, preserved in the curvature of space-time and delivered to our detectors over 7 billion years of cosmic travel. The gravitational wave signal from this event contains information about the masses and spins of the progenitor black holes, the geometry of the collision, the properties of the resulting merged object, and, encoded in the detailed shape of the ring-down waveform, the vibrational modes of the final black hole. These vibrational modes are specific predictions of general relativity, known as quasi-normal modes, and their measurement constitutes a test of the theory in the strong field limit. General relativity is extraordinarily well tested in the weak field, slow-motion regime of the solar system, and in moderately strong fields through pulsar timing and post-Newtonian effects. But the regime of two black holes merging at close to the speed of light, generating space-time distortions of order unity, is the most extreme regime accessible to any conceivable observation. Every gravitational wave detection is a test of general relativity in this regime, and every detection that matches the predicted waveform is a confirmation of the theory. So far, every event observed by LIGO and its partners has been consistent with general relativity. The constraints are becoming tighter with each new event as the statistical power of the dataset grows. GW231123, despite its unusual properties, also appears to be consistent with the predictions of general relativity, at least within the current uncertainties. This is both reassuring the theory continues to hold and potentially constraining for modifications to general relativity that predict deviations in the strong field regime. The precision tests of general relativity, enabled by gravitational wave astronomy, have already placed tighter constraints on certain alternative theories of gravity than any previous observations. As the catalog grows and the sensitivity of detectors improves, these constraints will tighten further. If general relativity does break down in the strong field limit, as some theoretical arguments suggest it must, given that the theory is fundamentally incompatible with quantum mechanics, at sufficiently small scales, gravitational wave observations are currently the most promising tool for detecting that breakdown. The interplay between gravitational wave observations and fundamental physics is thus not limited to the astrophysics of black hole formation and population statistics. It extends to the deepest questions about the nature of space, time, and gravity. Black holes are both astrophysical objects and laboratories for the fundamental laws of physics, and gravitational wave astronomy provides a way to study them as both. The fact that we can detect these events at all, the fact that a signal carrying information about a collision that happened over 7 billion years ago, involving objects that emit no light, can be measured by instruments on Earth as a subatomic wobble in the length of a 4-kilometer laser beam is, when considered soberly, one of the most remarkable achievements in the history of empirical science. And we are only at the beginning. The current gravitational wave detectors, extraordinary as they are, will be succeeded by instruments of far greater capability. The events they will detect, and the questions those events will raise, cannot be fully anticipated. The universe has repeatedly surprised scientists with observations that did not fit the prevailing model, and then provided the observations that eventually led to a better one. The two black holes that generated GW231123 collided when the universe was roughly half its current age, in an environment we cannot directly observe, through a process we are only now beginning to theoretically reconstruct. The gravitational waves they released have been traveling toward us for more than 7 billion years. When they finally arrived, they were so weak that they produced a change in the length of our detectors smaller than 1,000th the diameter of a single proton, and we caught it. The scientific work that follows from that detection, the theoretical models, the observational follow-ups, the next-generation instruments, the decades of analysis will unfold over many years and involve researchers who in some cases have not yet begun their scientific careers. What they will find and what they will discover that we currently cannot predict is the true measure of what GW231123 has set in motion. For now, the measurement stands. Two black holes that should not have existed merged billions of light years away, and the universe, in the process, gave us something new to think about. It is worth taking stock of what the science of gravitational waves has taught us more broadly about the stellar graveyard, the population of neutron stars, black holes, and white dwarfs that are the end products of stellar evolution. Before gravitational wave astronomy, our knowledge of stellar black holes came almost entirely from X-ray binary systems, where a black hole accretes material from a companion star, producing X-rays that can be detected by space-based observatories. About 24 such systems were known before LIGO began operations, and their black hole masses were estimated to lie mostly between 5 and 15 solar masses. This was a small and potentially biased sample. X-ray binaries are bright and detectable, but they represent only a fraction of all black holes. The majority of black holes are isolated or in binaries that are too widely separated to transfer mass, and these are essentially invisible in electromagnetic surveys. The LIGO catalog has revealed a black hole population that looks quite different from the X-ray binary sample. The typical black hole masses in merging binaries are notably higher. Many events involve objects in the range of 20 to 40 solar masses or beyond. This suggests that either the mass distribution of black holes extends to higher values than the X-ray binary sample implied, or that more massive black holes are preferentially found in the environments that produce merging binaries, or both. The mass gap itself between the maximum neutron star mass of roughly 2 to 3 solar masses and the minimum observed X-ray binary black hole mass of roughly 5 solar masses has also been examined with gravitational wave data. A handful of LIGO events appear to involve objects with masses with the neutron star to black hole gap, raising questions about whether these are unusual neutron stars, low-mass black holes, or something in between. GW 190814, detected in August 2019, involved the merger of a black hole with a compact object of roughly 2.5 solar masses, right in the supposed gap. Whether that compact object was a heavy neutron star or a light black hole could not be definitively determined from the gravitational wave signal alone. Electromagnetic follow-up observations found no counterpart, which is more consistent with a black hole than a neutron star, but the classification remains uncertain. These lower mass boundary cases and the upper mass boundary cases, like GW 231123, are both scientifically important in ways that go beyond curiosity. They define the extremes of the stellar remnant mass distribution, and the processes that create or forbid objects at those extremes reflect the underlying physics of stellar structure, nuclear reactions, and the mechanics of core collapse. Understanding both ends of the distribution simultaneously is necessary for a complete theory of stellar death and compact object formation. The neutron star equation of state, which governs the maximum mass a neutron star can achieve before collapsing into a black hole, is one of the central unknowns in nuclear physics. Theoretical predictions span a wide range depending on assumptions about the nature of matter at extreme densities, whether quarks become deconfined, whether strange matter is stable, how strong nuclear forces behave at densities many times that of an atomic nucleus. Observational constraints from pulsar timing have established that neutron stars can have masses of at least 2 solar masses, which rules out some of the softest equations of state. Gravitational wave observations of neutron star mergers constrain the radius of neutron stars, and thus the stiffness of the equation of state at intermediate densities. Together, these constraints are closing in on the true neutron star equation of state from multiple directions. The upper boundary of neutron star masses is connected to the lower boundary of black hole masses, and both connect to the core collapse process that determines whether a dying star leaves a neutron star or a black hole. The conditions that determine this boundary, the mass of the iron core at collapse, the energy of the supernova explosion, the fallback of material onto the remnant, are all active areas of theoretical and computational research. Three-dimensional simulations of core collapse supernovae have become increasingly sophisticated over the past decade, incorporating neutrino transport, magnetohydrodynamics, and general relativistic effects. These simulations have illuminated the turbulent, asymmetric nature of the explosion and the role of convection and standing accretion, shock instabilities in determining whether the shock successfully propagates outward or stalls and collapses back. But the precise boundary conditions between neutron star formation and black hole formation, and how they depend on the mass, rotation, and composition of the progenitor star, remain incompletely characterized. The Gottlieb simulation of GW 231123 progenitors sits at the intersection of several of these research frontiers. It studies a very massive star, well above the typical range of stars that are routinely simulated in supernova models, and includes magnetic fields in a way that has not been standard practice in most supernova simulations. The results point to the importance of initial stellar rotation and magnetic field strength as factors that can dramatically alter the outcome of the collapse, even for stars of similar initial mass. This finding is consistent with a broader trend in astrophysical simulations. Physical processes that were previously treated as secondary or were omitted for computational convenience, magnetic fields, rapid rotation, three-dimensional turbulence turn out to have first-order effects on the outcomes of some of the most important astrophysical phenomena. The lesson is that nature is more complex than simplified models, and the simplified models are sometimes wrong in qualitative ways, not just quantitatively. The specific way in which the simplified models failed for the mass gap prediction is instructive. The prediction was based on stellar evolution and nuclear physics that is well established. What it did not include was the possibility that a forming black hole surrounded by a rapidly rotating, magnetized accretion disk, could lose enough of the infalling material to magnetic field-driven jets to end up with a mass in the gap. The physics of those jets was not unknown. It had been observed in active galactic nuclei for decades. It simply had not been incorporated into models of stellar collapse. Connecting these two bodies of physics, the physics of accretion disks and jets around supermassive black holes and galactic nuclei, and the physics of stellar collapse, forming stellar mass black holes, is part of what the GW231123 result has motivated. There may be other cases where physical processes well established in one astrophysical context have been overlooked in another, leading to predictions that are incomplete in similar ways. Scientific fields are organized by tradition and technical specialization, and information sometimes flows slowly between subfields. The community studying active galactic nuclei and the community studying core collapse supernovae have different observational traditions, different theoretical tools, and different technical vocabularies. Breakthroughs often come when someone trained in one tradition recognizes the relevance of their techniques to a problem in another field. The team at the Flatiron Institute's Center for Computational Astrophysics is notable for bringing computational methods from the study of accretion disk physics to bear on stellar collapse problems. This kind of cross-disciplinary fertilization is increasingly common in astrophysics as computational power grows and as researchers have access to simulation tools that can capture multiple physical processes simultaneously. The interplay between theoretical predictions and observations in science works in both directions. Sometimes observations confirm predictions and validate the underlying theory. Sometimes, as with GW231123, observations challenge predictions and force theoretical revision. Both types of encounter are necessary for scientific progress. Without confirming observations, theories cannot be trusted. Without challenging observations, theories cannot be improved. The history of general relativity itself illustrates this. Einstein's theory was confirmed in 1919 by observations of light bending around the sun during a solar eclipse. But the most stringent test of the theory came decades later, from the observation of binary pulsar systems, pairs of neutron stars orbiting each other, gradually spiraling together as they radiate gravitational waves. The rate of this spiral, measured over decades of precise timing observations, matched general relativity's predictions to better than 1 part in 10,000. This was the first indirect evidence for gravitational waves, and it earned the observers, Russell Hulse and Joseph Taylor, the Nobel Prize in Physics in 1993. The direct detection of gravitational waves by LIGO in 2015 was the culmination of a line of scientific work that stretches from Einstein's prediction in 1915 through Weiss's detector concept in 1972 through decades of instrument development, through the indirect confirmation by Hulse and Taylor. The detection of GW231123 in 2023 is the latest step in a progression that is far from complete. The questions being asked at each stage have become more precise and more fundamental. In 1915, the question was, does space-time curve in response to mass and energy? By the 1970s, the question was, are there gravitational waves, and can we detect them? By 2015, the question was, what are the masses and properties of merging black holes across the universe? By 2023, the question is, why do intermediate mass black holes apparently exist when theory says they should not? And what physical processes are responsible? The next generation of questions, which the next generation of instruments will be positioned to ask, may be, do gravitational waves carry quantum mechanical information? Is general relativity the correct theory of gravity in the strong field regime? Do exotic compact objects, objects more compact than neutron stars, but less compact than black holes, exist in nature? What is the gravitational wave background, the cumulative signal from all the black hole mergers that have ever occurred? And what does it tell us about the history of the universe? None of these questions could have been asked, let alone approached observationally, before 2015. The entire program of gravitational wave astronomy exists because a series of experiments was designed, funded, and executed over a multi-decade timescale, in pursuit of observations that had not yet been made, and that some physicists considered might never be made. The courage and commitment required to build LIGO, to invest billions of dollars in an instrument whose scientific yield depended on black holes merging and producing detectable signals, with no guarantee that such events would be frequent enough to observe within any given time frame, reflects a particular kind of scientific vision. It is science conducted on the timescale of careers and institutions, not experiments. That investment is now paying dividends that exceed what the founders of the project envisioned. The gravitational wave sky turns out to be rich with events. Black hole mergers are not rare flukes. They are commonplace, happening multiple times per year within the observable volume of each LIGO observing run. Neutron star mergers occur at a rate consistent with theoretical predictions. And occasional extraordinary events like GW231123 appear with enough frequency to drive theoretical revisions and open new scientific frontiers. This is the state of the field in 2026. The instruments are operating, the events are being detected, the theories are being tested, and sometimes found incomplete. New theories are being proposed, and will themselves be tested by future observations. The intermediate mass black holes suspected to exist before GW231123 are now confirmed to exist, at least in one instance, and the community is working to understand whether they are rare exceptions or common occupants of the universe. The specific mystery of GW231123 will be resolved over time through the accumulation of more data and the refinement of theoretical models. The broader mystery it represents of how the universe populates itself with compact objects across all mass scales, and how those objects grow and merge to shape the structure of galaxies, will occupy astrophysicists for decades to come. And somewhere out there, right now, more black holes are spiraling together, preparing to release the last of their shared energy in a burst of gravitational waves that will roll outward through the universe, and eventually, perhaps, ripple past the Earth. Whether anyone will be here to detect them, and what they will reveal when they arrive, is a story still being written. One thread we have not yet pulled fully is the nature of the ring-down phase that LIGO detected in GW231123. The specific portion of the signal that was captured, and why it is both scientifically valuable and scientifically limiting. When two black holes merge, the process can be divided into three phases. The first is the inspiral, during which the two black holes orbit each other and gradually spiral closer, emitting a steadily increasing sequence of gravitational waves. The second is the merger itself, the moment of maximum amplitude, the plunge and collision as the two event horizons touch and coalesce. The third is the ring down, during which the newly formed single black hole is distorted from a perfect sphere and oscillates like a struck bell, radiating away the distortions as gravitational waves, until it settles into a stable, smooth configuration. For typical gravitational wave events detected by LIGO, all three phases are visible in the data to varying degrees. The inspiral can last many seconds at lower frequencies, before sweeping up to higher frequencies at merger. The merger itself is the loudest fraction of a second. The ring down decays over the following milliseconds. For GW231123, the situation was different. Because the black holes were very massive, the gravitational waves they produced during inspiral were at lower frequencies where LIGO is less sensitive due to seismic noise. The merger and ring down, which occur at higher frequencies, fell within LIGO's sensitive band. But the inspiral was largely invisible, which means that the most direct route to measuring the masses and spins of the progenitor black holes, tracking the evolution of the orbital frequency through the inspiral, was not available. This is why the mass estimates for the progenitor black holes in GW231123 have relatively large uncertainties compared to a typical lighter event. The team had to infer the progenitor masses primarily from the characteristics of the ring down, which encodes information about the final merged black hole rather than directly about the two progenitors. Mapping from final black hole properties back to progenitor properties requires additional assumptions and introduces additional uncertainty. The ring down signal, however, is scientifically precious for other reasons. The quasi-normal modes of a black hole, the specific frequencies and damping times at which it vibrates during ring down, are precisely predicted by general relativity. They depend only on the mass and spin of the final black hole, and they are a unique fingerprint of a black hole as defined by general relativity. This leads to a test known as black hole spectroscopy. If multiple quasi-normal modes can be measured in the ring down signal, each mode provides an independent measurement of the mass and spin of the final black hole. If all modes give consistent values, this confirms that the remnant is indeed a black hole described by general relativity. If different modes give inconsistent values, it could indicate that the remnant is not a standard black hole, or that some extension of general relativity is needed. Current gravitational wave observations have been able to detect the dominant quasi-normal mode in many events, but detecting subdominant modes, which are smaller in amplitude, remains challenging. This is an area of active research, and improving the signal-to-noise ratio of detected ring-down signals is a high priority for detector upgrades. GW 231123, despite having only the ring-down phase well captured, has relatively high signal-to-noise. In that phase, it was about 20 times louder than the typical noise level. This makes it potentially useful for spectroscopy tests. Initial analyses are ongoing, and results will be published in due course. The idea of using gravitational waves to perform spectroscopy on black holes, essentially measuring the resonant frequencies of a distorted black hole to verify that it matches the theoretical predictions of general relativity, would have seemed fantastical even 30 years ago. It is now a realistic experimental program. There's another aspect of black hole physics that gravitational waves have already begun to illuminate, and that becomes increasingly interesting in the context of events like GW 231123, the recoil kick imparted to the merged black hole. When two black holes merge asymmetrically, as happens when they have unequal masses, misaligned spins, or when the orbit is not perfectly symmetric, the gravitational waves are emitted preferentially in one direction. By conservation of momentum, the merged black hole recoils in the opposite direction. This is the gravitational wave rocket effect. For certain configurations, the recoil velocity can be surprisingly large. Numerical relativity simulations have computed that for highly spinning black holes with specific spin alignments, including some configurations similar to those in GW 231123, the recoil velocity can reach hundreds or even thousands of kilometers per second. These recoil kicks have important astrophysical consequences. A black hole that receives a kick of several hundred kilometers per second may be ejected from a star cluster, whose escape velocity is typically tens to hundreds of kilometers per second. This would remove the merged black hole from the environment where further mergers could occur, terminating the hierarchical growth chain. For the scenario discussed earlier, where the extreme spins of the GW 231123 progenitors are explained by hierarchical mergers in a dense cluster, the recoil kick problem is severe. High-spin black holes tend to receive large recoil kicks when they merge. Getting two very high-spin black holes to remain bound to their host cluster through multiple generations of mergers without being kicked away requires either an unrealistically dense and massive host environment or a specifically favorable set of spin alignments for each successive merger. This is one of the quantitative arguments against the hierarchical merger interpretation of GW 231123, and one of the reasons the magnetic field formation channel has attracted attention. If both progenitor black holes formed with high spins through the natal kick mechanism rather than through successive mergers, there is no recoil problem. The formation of each black hole is a single event, not a multi-step process requiring carefully constrained conditions at each step. The recoil kick received by the final merged black hole in GW 231123 is itself uncertain, because it depends on the progenitor masses and spins which are imprecisely known. But if the merged black hole received a substantial kick, it may have been ejected from whatever environment it formed in a globular cluster, an active galactic nucleus disk, or an open star cluster, and is now traveling through intergalactic space as an isolated massive black hole. There is currently no way to detect such an isolated, non-accreting black hole directly. The population of ejected merger products black holes in the intermediate mass range, drifting through the intergalactic medium far from any galaxy, is entirely invisible to current instruments. Their existence is inferred from the mechanics of gravitational wave recoil, but they leave no detectable signature unless they eventually encounter a gas cloud or another object to accrete. Estimating how many such objects exist and where they are distributed is possible in principle through population synthesis models combined with the LIGO event catalog, but the uncertainties are currently large. Future gravitational wave detectors sensitive enough to detect the ring down of an intermediate mass black hole merger in real time, combined with rapid localization from a multi-detector network, could, in principle, track the host environment of these events and compare expected recoil velocities with the properties of the environment. If intermediate mass black hole mergers are preferentially found in high escape velocity environments, like the nuclei of dense galaxies or nuclear star clusters, suggesting that only such environments can retain the merger products, that would be strong evidence for hierarchical growth. If they are found equally in low escape velocity environments, it would support the idea that the progenitors formed with high masses in single events. These kinds of statistical analyses require large event catalogs and precise sky localization, both of which will be provided by next-generation detectors. The scientific questions raised by GW 231123 are precisely the kind that the next generation of instruments was designed to address. There is something almost mathematical about the way scientific questions compound and elaborate themselves. Each discovery creates a set of sub-questions, each of which generates further sub-questions, and the structure of open problems in a mature scientific field can become extraordinarily deep and interconnected. Gravitational wave astronomy is a field that has been producing discoveries at a rapid pace for less than 10 years, and the depth of open questions it has already generated is remarkable. The detection of GW 231123 adds several new branches to this already complex tree. What is the relationship between magnetic field strength and the mass-spin correlation in black holes formed from very massive stars? What fraction of intermediate mass black holes were formed through this channel versus hierarchical mergers? Are there gamma-ray burst signatures in archival data that correspond to the formation of these progenitor black holes? How many intermediate mass black holes are drifting freely through the universe after being kicked out of their host environments by gravitational wave recoil? What role did intermediate mass black holes formed in the early universe play in seeding the growth of supermassive black holes? Each of these questions is tractable, in principle, given sufficient observational data and computational resources. None of them will be answered quickly. Each will require sustained effort over years to decades, combining theoretical development with observational programs that are themselves long-term investments. This is the nature of fundamental science at its frontier. The questions are hard. The answers require extraordinary tools and sustained effort. The timescales extend beyond the span of individual careers. But the questions are real, and the universe holds the answers. Every photon that reaches our telescopes, every gravitational wave that passes through our detectors, every particle that reaches our underground observatories is a message from nature. The task of reading those messages carefully, rigorously, honestly, is the work of science. GW 231123 is one such message, delivered in the curvature of spacetime itself, from a collision that happened when the universe was roughly 6.5 billion years old. We have read part of it. The rest is still being decoded. Among the many things that GW 231123 has prompted scientists to reconsider is the relationship between the stellar environments where very massive stars form and die, and the eventual gravitational wave events those deaths produce billions of years later. The cosmic timeline between stellar formation and gravitational wave detection is long and complex. A very massive star forms in a dense molecular cloud, perhaps when the universe is only a few billion years old. It lives for a few million years, burning through its fuel rapidly, then dies in a supernova or direct collapse, leaving behind an intermediate mass black hole. That black hole, if it is in a binary system, then spirals toward its companion over hundreds of millions to billions of years. If the companion is another intermediate mass black hole, the pair gradually inspiral until they merge and generate the gravitational wave event we detect today, 7 billion light-years away. The long delay between stellar formation and merger means that gravitational wave events detected today are sampling the compact object population that formed over a wide range of cosmic history. Events at greater distances correspond to earlier formation times. The light travel time, or in this case the gravitational wave travel time, tells us the cosmic age at which the event occurred. For GW 231123, the merger happened at a distance corresponding to a look-back time of more than 7 billion years, meaning it occurred when the universe was less than 7 billion years old. This is well before the peak of cosmic star formation activity, which occurred roughly 10 billion years ago, and before the present day when the universe is roughly 13.8 billion years old. The progenitor stars would have formed even earlier, perhaps 1 to several billion years before the merger. This means that the progenitor stars of GW 231123 formed in the early universe in a cosmic environment very different from today. Star formation rates were higher, galaxies were denser, and more actively forming stars. The gas from which stars formed was less enriched with heavy elements than today. These conditions favored the formation of more massive stars, and, potentially, the kind of very massive progenitors that could form intermediate mass black holes through the magnetic field mechanism. Understanding the redshift distribution of gravitational wave events, how the rate of black hole mergers varies with cosmic time and distance, is one of the key cosmological applications of gravitational wave astronomy. If intermediate mass black hole mergers preferentially occurred at high redshift, corresponding to the early universe, The rate of such events should increase with distance in a way that reflects the star formation history of the universe. Current samples are too small to see this trend clearly, but future detectors sensitive enough to detect many such events over a range of distances will be able to measure this distribution. This redshift distribution encodes information about when and where very massive stars formed, which is itself valuable information about the history of star formation in the universe. Complementary information comes from observations of the cosmic star formation rate, measured through the optical and infrared emission of star-forming galaxies at different redshifts. Combining these two independent probes, gravitational wave event rates, and electromagnetic star formation indicators, could provide new constraints on the formation history of very massive stars in particular. The James Webb Space Telescope has already detected individual very massive stars in nearby galaxies through gravitational lensing amplification, where the gravity of an intervening galaxy cluster magnifies the light from background objects enough to make individual stars visible. This technique has revealed stars with estimated masses of hundreds of solar masses in galaxies several billion light-years away. These observations are beginning to build a picture of the most extreme end of the stellar mass function at various cosmic epochs. If the population of very massive stars at high redshift is larger than current models suggest, which some James Webb observations seem to indicate, given the unexpectedly massive and luminous early galaxies that have been detected, then the production of intermediate mass black holes could be more common than the simplest theoretical models predicted. This would mean more gravitational wave events in the mass gap range than current extrapolations suggest. It is also worth noting that the formation of very massive stars is itself not fully understood. In the present-day universe, the formation of stars much more massive than about 150 solar masses is thought to be limited by radiation pressure. The intense radiation from the forming star disperses the gas cloud before enough material can accumulate. In the early universe, where the gas was cooler and less metallically enriched, and where the radiation environment may have been different, higher mass stars could in principle have formed more readily. But the details of star formation at the very high mass end are still debated. Direct observations of population 3 stars, the first generation metal-free stars, predicted to have been very massive, remain beyond the reach of current instruments. Even the James Webb Space Telescope cannot directly image individual population 3 stars at the distances where they formed. Their signatures must be inferred from the collective emission of entire early galaxies, or from the chemical signatures of the heavy elements their deaths dispersed into the surrounding gas. One of the long-term goals of gravitational wave astronomy is to detect the gravitational wave background, the cumulative stochastic signal from all the binary mergers that have ever occurred throughout the universe, superimpose on each other to create a diffuse gravitational wave noise. If detected and characterized, this background would encode information about the entire history of compact object mergers in the universe, integrated over cosmic time. The gravitational wave background from binary black hole mergers is expected to peak at frequencies around a few hundred hertz within the sensitivity band of ground-based detectors. Current LIGO observations have placed upper limits on its amplitude, and future improvements in sensitivity will move these limits toward the theoretically expected signal level. Detection of this background would constitute a new probe of cosmic history, complementary to the cosmic microwave background radiation that records the state of the universe about 400,000 years after the Big Bang. If intermediate mass black hole mergers contribute significantly to the gravitational wave background, as they would if such mergers were common in the early universe, their contribution could in principle be distinguishable from the contribution of stellar mass mergers because of the different frequency distribution. Intermediate mass mergers produce gravitational waves at lower frequencies than stellar mass mergers, so they would produce a characteristic spectral signature in the background at the low frequency end of the detector's sensitive band. This is another of the long-term scientific goals that GW 231123 has added motivation to pursue. By detecting this event, the community now knows that intermediate mass mergers do occur. The rate at which they occur, and the contribution they make to the gravitational wave background, are now observational targets rather than purely theoretical speculations. The connection between gravitational wave science and cosmology deepens further when we consider the space-based LISA observatory. LISA will be sensitive to gravitational waves in the millihertz frequency range frequencies, corresponding to the orbital periods of supermassive black hole binaries in the centers of merging galaxies, or to the gradual spiraling of compact objects into supermassive black holes. These in-spiral events known as extreme mass ratio and spirals, occur when a stellar mass or intermediate mass black hole finds itself in a tight orbit around a supermassive black hole and gradually spirals inward over thousands of orbits before finally merging. Extreme mass ratio and spirals are extraordinarily rich sources of gravitational wave information. Because the smaller objects spend so many orbits in the strong gravitational field of the supermassive black hole before merging, the gravitational wave signal encodes an incredibly detailed map of the spacetime geometry around the supermassive black hole. This is the most precise probe of the strong field structure of general relativity that any conceivable observation could provide. LISA is expected to detect hundreds to thousands of extreme mass ratio and spirals during its planned mission lifetime of several years. Among the inspiraling objects could be intermediate mass black holes, objects in the range of hundreds to thousands of solar masses falling into supermassive black holes. These would produce louder and more complex signals than stellar mass and spirals, potentially allowing measurements of the supermassive black hole mass and spin to remarkable precision. The discovery of objects like those in GW 231123 intermediate mass black holes of about 100 to 200 solar masses makes the prospect of LISA detecting intermediate mass ratio in spirals more concrete. If intermediate mass black holes exist in dense star clusters near galactic nuclei, some fraction of them will eventually find their way into tight orbits around the central supermassive black hole and generate LISA events. The relationship between the ground-based gravitational wave program and the LISA space mission is thus complementary in an important way. Ground-based detectors observe the final mergers of stellar mass and now intermediate mass black holes, probing the compact object population across the universe. LISA will observe the slow spirals and mergers of supermassive black holes and the feeding of small compact objects into galactic nuclei, probing the physics of the most extreme environments in the universe. Together, these programs span the full mass range of compact objects, from neutron stars at a few solar masses to supermassive black holes at billions of solar masses. The intermediate mass range, now confirmed to be populated, at least in part connects these two regimes and will be observable through both ground-based detections of intermediate mass mergers and space-based detections of intermediate mass objects spiraling into supermassive hosts. GW 231123 is therefore not just an anomalous event, it is a confirmation that the full mass spectrum of black holes is populated, and a demonstration that our theoretical models of where the boundaries of that spectrum lie were incomplete. This has implications that extend across the entirety of gravitational wave astronomy and astrophysics more broadly. The practical implication for observers is to prepare for more such events. The upgraded LIGO detectors in 04 and subsequent runs, and eventually the next generation instruments, will be sensitive to intermediate mass mergers at greater distances and with better parameter estimation. The community is already updating its signal analysis pipelines to be better tuned to the characteristics of high mass events, including the limited frequency coverage and the challenge of extracting spin information from ring-down dominated signals. The theoretical implication is to take magnetic field-driven formation channels seriously in models of compact object population synthesis. Population synthesis codes numerical models that simulate the formation and evolution of large populations of stars and binaries over cosmic time, are widely used to predict the rates and properties of gravitational wave events. Incorporating the magnetic field natal kick and mass shedding mechanism into these codes, and varying the parameters that govern it, will produce new predictions for the intermediate mass event rate and the mass spin distribution that can be compared with observations. If the predictions match the data as more events accumulate, the mechanism will become established as a genuine formation channel. If they do not, further theoretical development will be needed. This back and forth between prediction and observation, between theory and experiment, is the engine of scientific progress in any empirical discipline. We are watching that engine run in real time in gravitational wave astronomy. The field has moved from first principles, through instrument construction, through first detection, through the accumulation of a substantial catalog, and now to the discovery of objects that challenge our theoretical models. The cycle is working as it should. The universe is under no obligation to conform to our models. What it does instead is provide data, which constrains models, which generates new predictions, which require new observations, which produce new data. This cycle does not end. It only deepens. 7 billion light-years away, in the darkness between galaxies, two massive and fast-spinning black holes met. The merger lasted less than a second. The ripples lasted 7 billion years. When they arrived, we had instruments precise enough to detect them, physicists skilled enough to analyze them, and theorists capable of proposing new mechanisms to explain what they revealed. That alignment, the readiness of the science to receive the message the universe was sending, is not an accident. It is the result of decades of sustained scientific investment, intellectual curiosity, and the willingness to build extraordinary instruments in pursuit of observations that had never been made. GW231123 is the latest demonstration of what that investment has made possible. It will not be the last. Let us close by considering what the next 5 to 10 years of gravitational wave science is likely to deliver, and where GW231123 fits into that larger trajectory. The LIGO-Virgo-Cagra collaboration is currently in its 4th observing run, expected to continue through mid-2025. By the time this run ends, the event catalog will likely contain well over 500 gravitational wave events, covering a wide range of source types and parameter values. This dataset will enable statistical studies of the black hole mass function, the spin distribution, the merger rate as a function of redshift, and tests of general relativity across dozens of events simultaneously. Within this catalog, researchers are particularly alert to any additional events that fall in or near the mass gap. Even 1 or 2 more confirmed intermediate mass events would substantially strengthen the case for a formation channel like the one proposed by Gottlieb and colleagues, and would begin to constrain the rate at which such events occur. A handful of events would allow preliminary tests of the predicted mass-spin correlation. The 5th observing run, currently planned for the late 2020s, will incorporate further hardware improvements that are expected to extend LIGO sensitivity by another factor of roughly 2 in amplitude, corresponding to an 8-fold increase in the detectable volume. This will dramatically increase the number of detected events and push detection distances well beyond the current range. Intermediate mass mergers will be detectable at higher redshifts, sampling the early universe when very massive stars were more common and conditions more favorable for their formation. Beyond the 5th observing run lies the next generation detector era. The Einstein telescope and Cosmic Explorer proposals represent a quantum leap in sensitivity, roughly 10 times greater strain sensitivity than current LIGO in their design frequency bands. At this sensitivity level, essentially every black hole merger in the observable universe becomes detectable. The event rate would shift from hundreds per year to hundreds of thousands or millions per year, depending on assumptions about source population rates. At this rate, gravitational wave events would cease to be individually analyzed and would instead be studied statistically. The entire gravitational wave sky would be a continuous map of merger activity across cosmic history. The intermediate mass black hole merger rate would be determinable to high precision, and the evolution of that rate with cosmic time would be measurable. This would connect gravitational wave observations directly to galaxy formation and evolution science. The rate at which galaxies form stars, the masses of those stars, and the environments in which they form all influence when and where compact object mergers occur. Measuring these rates as a function of redshift and comparing them to electromagnetic observations of galaxy properties at corresponding epochs would provide a new and independent probe of cosmic history. The space-based LISA mission, with its planned launch in the mid-2030s, adds another dimension. LISA will detect the mergers of supermassive black holes in colliding galaxies, events currently completely invisible to any instrument, along with extreme mass ratio inspirals and potentially the mergers of intermediate mass black holes in the millihertz band. The combined coverage of ground-based and space-based detectors would span the full range of astrophysically relevant gravitational wave frequencies. This future is not speculative. The instruments are being designed. The funding processes are underway. The scientific community is preparing the analysis techniques and theoretical frameworks that will be needed when the data starts flowing. The legacy of GW231123, the event that confirmed intermediate mass black holes exist and showed that the mass gap is not truly empty, will be one motivating factor among many as these programs develop. For the researchers working on these questions today, the window between now and the next generation of detectors is a period of building the theoretical and observational infrastructure needed to make the most of the data that will arrive. Models of black hole formation need to be made more comprehensive. Population synthesis codes need to be updated. analysis pipelines need to be developed that can handle the higher event rates of future runs. The science of gravitational wave astronomy is in a rapid growth phase, and the investments being made now will determine how well the community is positioned to interpret the data of the next decade. GW231123 has given that community a concrete target. Understand the mass gap, understand what fills it, and understand what intermediate mass black holes tell us about stellar physics, galactic evolution, and the history of the universe. The signal lasted a tenth of a second. The scientific program it launched will last for years. The most honest summary of where the science stands today is this: we have detected something that should not exist according to our best previous models. We have a plausible physical mechanism that could explain it, grounded in well-understood physics, applied in a new context. That mechanism makes specific, testable predictions that future observations will either confirm or refute. And the detection itself has opened new questions about the distribution of intermediate mass black holes in the universe, their role in the formation and growth of supermassive black holes, and their potential contribution to the gravitational wave background that future detectors will seek to characterize. The science is advancing on multiple fronts simultaneously: theoretical modeling, instrument development, observational program planning, and the analysis of existing data. Progress will be incremental at first. A few more events here, a refined model there and then, when the next generation instruments come online, potentially dramatic. What the universe has shown us with GW231123 is that the mass gap, long thought to be a permanent absence in the black hole population, contains at least some residence. Whether it is sparsely populated or moderately filled, whether its inhabitants formed through the magnetic field mechanism or some other channel, and what their existence implies for the history of stars and galaxies. These are the questions that carry the science forward. The signal from November 23, 2023 will continue to yield scientific returns for years. Papers are still being written about it. Analysis techniques are still being refined. The community is still in the process of fully characterizing what it observed. But even at this early stage, its significance is clear. It is a direct detection of the theoretically forbidden, and therefore an invitation to build better theories. That invitation is exactly what science is supposed to produce. The story of GW231123 is ultimately not just a story about two black holes colliding. It is a story about the process of scientific discovery, about building instruments of extraordinary precision over decades, about theoretical predictions being tested and found incomplete, about the way a single unexpected observation can reshape a field's understanding and motivate new directions of inquiry. In 7 billion years, those gravitational waves crossed galaxies, traversed voids, passed through the large-scale structure of the universe, and ultimately arrived at a pair of detectors sitting in the Louisiana and Washington countryside. The humans who built and operated those detectors did not know what they would find. They had built the instruments to see whatever the universe had to offer. And what it offered was something unexpected. Two black holes that theory said could not exist, merging to produce one that can. That is the nature of discovery. You build the window, and then you look through it.